I'm going to be talking about drawing graphs. Up until now, we've been discussing various properties that the graph of a function might have, and we can combine these with properties of functions that we've learned before to sketch out graphs of functions that we want to study, which have all of the important features in the graph. So say you want to graph a function f. The first thing to look at is the domain of the function. That is, we want to determine where the function f is defined. Once we've done that, we should look for vertical asymptotes. Since we already know the domain of f, we should be able to locate any isolated points that are not in the domain, and then check the limit of the function as it approaches those points to see if there's any asymptotes. Next, we should study the behavior of the first derivative of the function. By looking at this, we can check to see where the function is increasing, where it's decreasing, and whether there are any minima or maxima, local or global. Another thing we can look for, given the first derivative, is vertical tangent lines. Once we know the first derivative, we know where the first derivative is not defined, and if we look at the limit of the derivative close to those points, then we can determine whether there are vertical tangent lines if it goes off to infinity. After we're done studying the first derivative, we can start looking at the second derivative tests. By observing the second derivative, and whether it's positive or negative, we can determine when the function f is concave and when it's convex. And we can also determine if there's any inflection points and where those are. After doing that, we can look for horizontal asymptotes by checking the limit of f as it goes to either infinity or minus infinity. And finally, we can try to find the intercepts, so the x and y intercepts, or where the function intersects the x and y axes. So when graphing a function, we can go through each of these steps in this order to search for all of its interesting features so that we can draw an accurate graph. Let's look at a simple example of this to see how it works. Let's say our function is f of x equals x squared. The first thing to find is the domain. The domain of this function is just all real numbers. That's because we can take the square of any real number and it's still a real number. Now the next step is vertical asymptotes. Since f is defined everywhere, we don't have to look for any of these. Let's move on to the first derivative. F prime of x is equal to 2x. So any critical points are at 2x equals 0, so x equals 0. Also, f prime of x is less than 0 if x is less than 0, so decreases on the interval minus infinity, comma 0. Similarly, f increases on the interval 0, comma infinity, since 2x, or f prime of x, is larger than 0 whenever x is larger than 0. Since f decreases all the way up to x equals 0, and then increases after x equals 0, that means x equals 0 must be a local minimum. In fact, we know that f of 0 is equal to 0, and f is larger than that, or increases forever on both sides, so 0 is also a global minimum. Now for the second derivative. F double prime of x is just equal to 2. Since 2 is positive no matter what x is, we know that f must be convex. And it's never 0, so there's no inflection points. Now as x goes to infinity or minus infinity, f goes to infinity or minus infinity. This means that there's no horizontal asymptotes, and there's no global maximum. Finally, at any y-intercept, we have f of x equals 0 squared, which equals 0, and at any x-intercept, we have 0 equals x squared, which implies x equals 0. Now that we have all this information, let's put it together into a graph. Let's draw our axes here. Now the function comes from infinity on the left side, and it's convex, so it'll be curving upwards like this, while decreasing until it hits its global minimum here at 0, and then it's still convex and increasing like this. So as we already know, this is what the graph looks like for f of x equals x squared.